Why are you frowning tonight, Michael? Okay, it is 6 o'clock, so why don't we get underway here? Give me a green circle if you can hear me okay. I think most people can. Okay, I don't see Numa or Al. No.
I'm here, Professor. The mayor.
Okay. Okay. I'm not going to collect the homework tonight. I'm going to trust that you got it done. Let me see here. Just as kind of a did you get it right type of a thing. I very, very quickly, and I could have wrong answers here, which is okay because it's mostly showing you what I'm formatting out of the thing. I did it once with D flip-flops. So I said D1 was equal to S1, not S0, not I0, or not S1, not S0, I0, or S1, S0, I0, or not S1, S0, not I0. Now, I might have gotten that wrong. I didn't double check it. But the first term gave you kind of an exclusive or kind of a pattern in your boxes. So that would have been one of the three answers you had to give for that particular problem. D0 was simple on mine, the version I did. It was just not S0. And of course, the final output was just equal to S0. So those would have been the three equations that solved the homework if I was doing the D. And to be honest with you, I drew the chart from memory, so I may not have worked the same problem you did. But roughly, this is the type of answer you should have done. With JK, you'd have had a J1 and a J0, a K1 and a K0, plus the output. And with the T, you'd had a T1 and a T0 and a O0. Anybody have any question about that? Okay, now, you might say, well, the only thing important here is the output. Why don't I just get rid of everything else and make QZ or O0 be the S0 and be done? Well, the reason is because internally, part of the use of the state machine is that we also have access to these other state variables. And while we're just showing one of the outputs here, there could have been a whole bunch of outputs. And the idea is that we want to be able to put the outputs out in some sort of a sequence, possibly controlled by some number of inputs. So we really do need all three equations. and we try to minimum sum of products for them so that they become easier to implement. Okay, well, I got a whole stack of papers here today that we have to talk about. So let's do the practice exam just so we can see what needs to be done with that. You find your name on that list and then look to the left of it. That's the name of the exam you're going to be taking. If you want to download this list so you're sure you're getting the right one, let me see if I can find it here. That's the file I just downloaded. So find your name on here. You want to pay attention to a couple things. One is make sure that it says exam 0, because you could have a different number for exam 1 or exam 2 or whatever. And also look at the number itself. You're identified by this last number. So I'm going to be Samuel. If I'm Samuel, I'm number 21. Nobody else is number 21, only me. My exam has been customized so that the right questions for Samuel are on that particular exam. Anybody have any question about what the name of your exam is going to be? Jay?
Yeah, it's saying access denied for me.
For this file?
Yeah.
Well, then you typed something wrong, because if I can get to it, you can get to it. I don't have any special privileges. And plus, you can really just read it off of here. Here's all the numbers and things you need. Now, when we take the exam, what you're going to do is you're going to go to the test directory and you're going to download this file. From that point forward, you're not going to cheat, and you're going to turn it in once you've gotten the exam completely filled out. Now, you don't know where that folder is yet, so you can't download it, but we will talk about that in just a second. Sharon?
Yeah, I cannot download. Just you said it gives me an error when I put it.
It should.
I cannot. I'm taking an error.
Yeah, and it should. You should have an error at this point because we don't know where to download it. Okay, now, when you get the exam, what you're going to do is you're going to use the name you have. It doesn't look like Samuel's here, so I will be Samuel tonight. Grab the name of your exam. Just go to the website. Okay, this is our website. Put a slash. And then for this particular exam, you need to type the letters lowercase EX. Put a slash, and then paste in the name of your exam. And you should be able to go there. Now, you're not 21. I'm 21, so don't copy exactly what I put on my screen. Give me a green circle once you've gotten it up on your screen like this. Make sure you have your exam and make sure it came from the EX directory. Now, when you did this, it may come up on your window or it may download into a file. Either one of those two things could happen. If it comes up on the screen and you're on Windows. If you're on a Mac or Linux, you're up to figuring out how to make this work. But if you're on Windows, you can just right-click on the Google browser, go to Save As, and then what you probably want to do is put it on your desktop. Now, I actually have to navigate to get to my desktop. And you'll notice the name of it now should be exactly the name that was on the assigned sheet. Mine says exactly exam_0_21.txt. Yours will say the same sort of thing, and it'll make sure it's a text document. You don't want any PDFs or RTFs or XLSs or anything like that. It has to be a text document. And then save it. And I would save it to the desktop. Now I have to find it on my desktop. Here it is. I can't drop it there. And when I open it up, I'll find my exam. Now yours will be similar to mine, but this is the front piece for first 4 questions of one of last year's exams, I believe. Now, this is the file you'll take the exam in. This is the thing you're going to turn in. You're not going to use the thing that was in the web because when you downloaded and saved it, you created a .txt file. It's very important that this have exactly the right name, .txt, or else you won't get credit for the exam. You'll have to take it again. Now, when you get it, it'll have an exam number at the top. It'll have some funny numbers down at the bottom. Don't mess with those. Then it'll have some number of questions. I think the first one has about 20 or 30 questions on the first exam. This one only has 4. What you will do is you'll type your answers in between the angle brackets. You won't type anything else, and listen to me carefully about this. Nothing else gets typed on your exam except for your answer between the brackets. Don't put any extra new lines or anything inside of the brackets. Your answers will fit on a single line. And don't put any angle brackets inside the angle brackets because you'll break the auto grader. And those guys get really mad if they have to hand grade one of these. So what's my name? I'd click between there. I would take it in the tester. My name is John, whatever it is, John Watson. Not really. I spelled it wrong. I get a flunk. So that's almost a guaranteed right question for you. If you can spell your name, which I'm having trouble for here, if you can spell your name and get it between the brackets, you probably got question 0 right. Second question on mine says encode stars 57 into ASCII using odd parity. Put the answer in hex. So I'm going to make up some numbers here. 1, 2, 3, 4, 5, 6, 7, 8. Maybe that's what stars 57 is. This would have the odd parity bits on them. This would be my hexadecimal answer. How much current's passing through a 2.7 k ohm resistor that's dropping 4.5 volts? Express your answer in decimal with 2 digits of significance. Very important that you follow what it says. Okay, and so let's say that it was 3 millivolts, but it was 3.0 millivolts. Or actually current, milliamps. There'll be 2 digits here because it says 2 digits of significance. Remember, leading digits are never significant. Then finally, it says encode the hex Unicode code point of 200, which is in hex, into UTF-8. Express your answer in hex. Remember, UTF-8 is specified in bytes, so that might be the answer. So what I want you to do now is I want you to take your test. We'll take 5 minutes. When you're finished with it, make sure you save it. Then you're going to email me this file. Now, this file needs to be attached, not shared, not cut and pasted, not converted to some other format, but this needs to be attached to the email. The email subject needs to contain COS 231 exam 0. And the actual body of the text itself can contain the same thing as the subject if you want, if you get anything. It has to be mailed from your Mercer email to my Mercer email. Anything else will get rejected. Okay, give me a green circle if you understand the rules. And I have 6:14. I'll give you to 6:20 to get that done. If you get done, just hang out and, enjoy a little bit of your coffee. And this is don't share the answers, so don't talk to anybody else about it. And that'd mean in our chat or in Discord or Twitch or anything else that you might be connected to somebody. Exam is to be done all by yourself, including this one. Miguel, you have a question?
What's the email address so I could send a thing?
Look on the syllabus.
Okay.
I don't send myself enough mail to know. Okay, let's try to wrap it up in the next minute or two. Mohammed,
Professor, what should be the subject for the?
COS 231 exam 0.
Okay, thank you.
Okay, whether you're done or not, go ahead and email me what you have so I can see that you can do the email process. Doesn't matter if you're not done, you haven't completed the questions. Sargon, you have a question?
Just Professor, would we be receiving any kind of reply?
Not tonight.
Okay.
Okay, we have to move ahead, and if you don't have yours turned in, you're going to get behind. So give them to me whether or not you finished them. Okay, I'm not looking at who's turned anything in. Does anybody still have a paper? Submit whatever you have. Okay, well, we got to continue ahead here. We'll be sitting all night waiting for the one or two people that are still trying to figure out what their name is. That should have been representative of the type of question you might be seeing on the first exam. Remember that in the real situation, we're going to do what somebody asked about is when you send it in, one of my tech assistants here, Tom, is going to send you back the word thanks. Once you've received the word thanks, you're done for the evening. The test is over for you. If you don't receive it, I'll have given you a time to return back to the room. Normally, we'll leave the room while we take the test. And then you'll come back in only if you don't get the word thanks from Tom, you know, at a reasonable amount of time after you submit it. I mean, at the last minute, we'll get, 15 people all submitting at once, and he's only one person. So he may get a little behind on sending the thanks. But what you'll do is you'll come into the room and wait until we verify that we got a good, solid copy of your exam. And you can use the thanks as the receipt that you sent something in. Now, doesn't mean you send it in correctly. We're hoping tonight we'll catch the people that are likely not to do it correctly. And usually we have one or two people that just have problems and can't get it done. But maybe not this time. Maybe we'll go for a perfect score this time. Give me a green circle there if you think you got at least 3 out of the 4 questions right. Okay. How many people think they got all 4 of them right? Again, give me a green circle for that. And a red if you don't. Okay. Means there's some studying to be done. Let me remind you, I will be doing, unless something happens that I can't, a study session for anybody that wants to join me on Thursday evening at 6 o'clock, normal place in this room. And it'll be a relaxing, let's just study. And it's not extra credit, meaning if you come, it doesn't help your grade any in terms of extra credit. You might get some extra, you'll have learned more, so you may do better on the exam, but that doesn't, it's not critical you be here. And the other thing is that if you're not here, there's no punishment for not being here. It's if you're here, you're here. If you're not, you're not. I'm going to do a review whether anybody's in the room or not. And you don't have to stay the whole time. You can come for 10 minutes and leave, or you can stay the whole time with me and ask questions. It's just really just for you in case you think you need a little extra study time. The exam itself will be Monday night, pretty close to 6, so try not to be a drifter. And those people that have accommodations of some sort, just tack the extra time onto the end of it. Whatever time I give the rest of the class, you get either 1.5 times or 2 times, depending on what your accommodation is. And of course, you won't return to the room in that case. You'll have to wait for the thanks and exchange email if something is not received. It'll be up to you to make sure that your homework or that the test gets turned in. And that's for everybody, not just the accommodated people. Anybody have any questions about the exam so we can move on? Sergeant, is your hand up or was that still up?
No, I have a question.
Okay.
Like for the midterm, how are we supposed to submit our working for the questions?
Your exam will be exactly like the one you took. There may additionally be another question which is turned in separately, which is a programming assignment.
Okay, so we're not supposed to show any kind of working to you?
You're supposed to have the work ready. So if I get suspicious that you were copying off of an online calculator, I may ask you to submit work. So you probably want to keep a copy of what you did on another thing, but it's not to be turned in. with the exam. You do exactly like you did here. Only the answer goes on that sheet of paper. And that's so we can get your grade back sooner for you, particularly for people that might need to withdraw before the time is up for that.
Okay.
Mohammed?
Professor, do all questions carry same amount of points or
No, they didn't. They do not.
okay?
Dante?
Yeah, I was just wondering, do you know roughly how many questions will be on the exam? Like what sort of like are we looking at like 30 questions or like something more like the 100 question range?
For this exam, I think, I don't have a copy of it with me, but I think it's between 25 and 30, somewhere in that range. The general thinking for an exam should be that you have about 2 to 3 minutes per question, averaged out across all the questions. Because some of them are just like, give me the ASCII character for, it takes you 15 seconds to do if you memorize the stuff we ask you to memorize. If you didn't, or if you do what I told you not to do, which is to take a note and have to go through all the notes again, you're going to not finish. But if you did the stuff and memorized the things I asked you to do and did all that, you'll meet the time things. It'll seem like there's almost not enough because it's time down to having the average student finish exactly, on time. And there's really no overtime for this because I need to have the test back and you need to have gotten a thanks from the tech here to verify that it was turned in and ready to be graded. Any other questions? Did that answer your question, Dante?
Yes, it did, Professor. Thank you very much.
Okay. Anybody else? I hope everybody's excited. I think I might even take it myself. I haven't seen it in a while. I may sit here and take the test and see what grade I get. I'll never tell you if I've missed any questions, but what the heck? You've seen that I can make mistakes, so I probably could. So I'm going to make sure I do the best I can on as many questions as I can. And then the ones that I just absolutely don't know, I may have to guess. And let's hope that there's not a lot of those. Okay, are you guys ready for me to move ahead? Okay. And like I say, this Thursday, if you want to have some review with me, I'll be here and we can do that. And for some people, that helps them out because it'll relax you a little bit about having seen some of the questions types. I won't have the exam yet in my hand, so I won't even know what the questions are. But those 4 you just got were from an exam given at exactly the same time of year last time. So the questions will be similar to those, at least at the start of the test. At least the first 4, we kind of have a clue as to what they might look like. Okie dokie. Everybody remember this thing? Oop. Geez, I can shrink that down. We had a register which had 4 bits in it. And with those 4 bits, we could select, using these as though they were address lines, one of these AND gates over here. And as long as the number was between 0 and 9, because we only have 10 lines here, one of these outputs would turn on. Everybody remember that? Kind of give me a green thing. This was under digital components when we talked about this. This is sometimes called a data or a 1 of 10 decoder. Well, actually, that's on this sheet here, so that's what it's physically called in our world. If one of the numbers is picked that doesn't have an output, well, nothing turns on. All the outputs would be turned off. So normally we would constrain the outputs here to stay within the bounds of 0 to 9. So we could select one of the outputs. Now, typical use of this in a microcomputer might be to decode an instruction. Let's say we have an instruction which we could store in 4 bits here, and then have each of these come on if that's the instruction we're currently trying to execute. Maybe it's a load, maybe it's an add, maybe it's a subtract, maybe it's a move, maybe it's a halt. Whatever those are, and then further logic over on this side could decode what it's doing used to this, because you can imagine that the steps you do to do an add must be different than the steps you do to do a halt. So this is a pretty handy construction to know about. But there's one other thing we could do with this, which is a little fancier. We could hook it up. Let's see if I have it over here somewhere. Like this. Now notice the difference in this one. We now have 5 input AND gates. We still have the 4 address lines, and we've expanded it to have 16 possible. So all possible combinations of these bits will cause one of these AND gates to be selected because all of its inputs will be 1, except for the last one, and we'll zoom in here, which is hooked to a data line. If that data line is 0, then even when all the other lines are 1 here, a 0 will come out. However, if that line is ever a 1, then if all the other lines become 1, a 1 can come out. So just like the last one, we're selecting one of these AND gates, but the output we put out is based on the input we put in over here. And all these, of course, get ORed together to produce the final output. Okay, my screen has gone into flicker mode. Let me see if I can make that come back. Give me a green circle if you guys can still hear me. Okay, I thought I might have been booted off. Now, this is kind of handy because what that says is we could take and set an address and take a piece of data at that address and put it at the output. So really we could modify our picture to look like this. This is sometimes called a data selector, but it's more properly called a multiplexer. Now this is kind of cool because if you think about it, we can generate any Boolean function of 4 inputs over here, pretend like that's A, B, C, and D, by putting the truth table, the Y values, on this guy's inputs. So if I had a truth table that said at 0, 0, 0, 1, I wanted to have a 1, well, here's the 1. Meaning if I ever put 0, 0, 0, 1 here, I'm going to route that 1 through the chip to the output. So without doing any Karnow reduction or anything on this, we're able to generate any 4 input Boolean function using a multiplexer. Now you might say, well, why don't we use multiplexers all the time? And the answer to that is they're not as fast or as efficient as wiring the circuitry using logic gates. The other thing is, because we don't do any Karnowing of the thing, it could have been, we could have done it with a smaller multiplexer if we'd spent the time to do that. So often before we place it into the multiplexer, we're going to decide what the minimum equation is that we need to actually represent. And maybe we could get rid of one of the outputs, or we get rid of the D if we only need A, B, and C. And then there'd only be 8 inputs, and we'd be doing an 8-to-1 multiplex. Now, kind of the original purpose of a multiplexer was, imagine that I have a building, and in the building I have 16 computer keyboards. And I want them all to share one transmission line that goes to another building. I could hook each of the keyboards to one of these lines. And then repeatedly, I could cycle through 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And it would cause whatever's here to appear on this line in turn. So I'd get keyboard 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 15. And then I'd repeat 0, 1, 2, 3. And if on the other end, other end, I had something called a demultiplexer, DE multiplexer, it could take and return back from 1 bit to the original 16 inputs that I had. So I'd be able to encode and decode to a single stream some parallel data into a serial stream and recover it using a multiplexer and demultiplexer. Right now, however, we're going to focus in on using this thing to generate a Boolean function, because we're going to find that that's kind of a handy thing to be able to do. Now, we also can multiplex, and you'll see the term done for this purpose. In this case, I'm going to have two registers, register L and register R. Each of them are 4 bits in size. I'm going to have a control signal called write. When write becomes a 1, then whatever is on this side will be routed through to the outputs. If write is not asserted, meaning left, then whatever is on this side will be routed through. So I can take some number of outputs, which were driven by some number of inputs, and pick which one I want to appear at the output. Now, in combinational logic, that doesn't do anything because it's one or the other. But with sequential logic, we could alternate back and forth between either this 4 or that 4. And as long as whoever was receiving you knew what right and left was, maybe they're controlling the signal, they could take and get either half of the data and process it the way they needed it. So this is another use. We call this a nibble multiplexer because it multiplexes a nibble at a time. This is another way, if you had 8 bits of data, to be able to pass it to the next stage 4 bits at a time. Right half, left half, right half, left half, where you change the data right before you do the right half each time. So that's kind of the game plan for multiplexers. And what we want to look at now is, if we were going to be using these, how could we use them to generate a Boolean function in some sort of a controlled way, because we might be asked to do that sometime soon. Let me put this back where it came from. What was this? It was an exam. Let me stick it over there. So let's look here at a multiplexer and how we might use it. First of all, the square box is going to represent a multiplexer. Now, we know we could build one out of NAND gates if we needed to, but we also could out of ANDs and ORs and NOT gates, or more sophisticated, we could just buy a TTL, a multiplexer. The multiplexer has as its inputs some number of values. So these values are what are going to get routed, the D0, D1, D2, or D3. They're going to be routed over to F. Which one gets routed is based on the number of control inputs. Now, the control inputs say which one of these is going to be placed on F. So if I say 0, 1, then D1 gets placed on F. If I say 1, 1, then D3 gets placed on F. Now, in order to tabulate that in a table, I can describe that thing I just said by saying, if A and B are 0, 0, F is equal to D0. If A and B are 0, 1, it's equal to D1. If it's 1, 0, it's equal to D2. And if it's 1, 1, it's equal to D3. Therefore, we know how many data inputs we need by taking 2 to the number of control inputs. We have 2 inputs, so 2 squared is equal to 4. That means we'll have 4 inputs, or basically 4 lines in our truth table. Now, this table, its function is below. the function we're going to see is a function of A, B, and D. It's really, because D could be 1 or 0, it's the same as if we had 3 inputs here driving F, where the inputs are the invert, which is 0, 0, and whatever D is, the 0, 1, and whatever D is, 0, 1, 0, and whatever, well, 0, 1, and whatever D is, and 1, 1, and whatever D is. So that supports what we just said. This table represents this function if we don't know the values of D in advance. If we know what they are, we can just wire in 1s and 0s, and then we in fact know what F will be if we change A and B to these values. We just have a normal truth table then. So here's how that might be implemented using a multiplexer. And the multiplexer here is going to use AND gates, OR gates, and inverters. And we could, of course, build this out of NANDs if we wanted to. We just won't in this example. We might on an exam, though. So make sure you've practiced doing that, turning these various things into NAND gates. A and B, pick which one of these 4 is going to be the one we're considering. And the way they do that is they're going to make 2 of the inputs on the AND gate equal to 1. So if A and B are both 0s, the 1s are going to come out of the inverters. So the inverters will be tied to here and here, meaning that this becomes the hot gate. And the only thing that's going to determine now what its output is going to be the value of D0. So if I select this AND gate using this, then D0 is either a 0 or a 1. If it's a 1, it will pass through the OR gate to F. If it's a 0, since none of the others can be a 1 because they've not been selected, meaning they have at least 1 0 on one of their lines, they could never produce a 1 while this guy's selected. Then the 1 is completely controlled by D, and F is equal to whatever D is. And we could go through for each of the gates and see that each one can be selected by different combinations of A and B. So let's say we have the majority function, which we've talked about before. We have 3 inputs, A, B, and C, which are our control lines. We know there's got to be 8 lines in the truth table. Here they are. M is the majority function. We could have called it Y. But M says put a 1 in the output anytime there's more 1s than there are 0s. So here there's more 1s than 0s, so there's a 1. There's not. And all the rest of them, there's more 1s than 0s. Now, in order to get this multiplexer to work, all we have to do is wire each of the outputs of the truth table, and each in between, to the inputs of the multiplexer. Then when we pick a particular A, B, and C, the correct Boolean function output will pass through to F. Give me a green circle if you sort of understand that. Okay, Jay, do you understand that?
Yeah, a little bit.
Okay, how about you, Yan-Wen?
I don't know.
Okay, well, let me grab a notepad here. That looks like an old test we can get rid of. I'm going to have a truth table of A, B, C. And I'm going to produce an output, call it Y, which is 0, 1, 1, 1, 1, 0, 0, 1. Now I want to build a multiplexer that is going to be representative of that particular function. So I go to my box of multiplexers, and I get one that has 3 inputs, A, B, and C. And it has an output Y. Now, because I have 3 inputs, that means I can select 3 lines. So I could have 0, 0, 0. I could have 0, 0, 1, and so forth until I get down to 1, 1, 0 and 1, 1, 1. There'd be 8 lines. Now, I'm going to hook to each of these, and there's a bunch of lines in between. 1, 2, 3, 4. There's 5, 6, 7, 8. There's 4 more. I'm going to hook 0, 1. Then in the middle here is 1, 1, 1, 0. And then finally, 0 and 1. So whenever I pick A, B, and C, these first 3, it of course is going to get the right answer because I put the right answer wired to the right place. So 0, 0, 0 is supposed to give me a 0, and I wire a 0 there. Then the 0 is going to pop out where Y is. Okay, you should be reasonably clear about that. That's not too confusing. We can make it more confusing, but probably for now we probably shouldn't. Okay, let's move ahead a little. Now, what we want to try to do is shrink the size of the multiplexer we need to solve the same problem. And we're going to do that by making an observation. And here's the observation. Notice that every 2 rows of the truth table have A and B being the same value. And notice that if we take C into consideration in the first 2 here, it doesn't matter. F is always a 0. And in the second 2, if we look at F, it didn't matter what C was. It's always a 1. And here's a little more interesting one. If we have 1, 0, it does matter what C is because the output is exactly what C is. And probably unsurprisingly, if we have 2 1s and the output is 0, and this is a 1, it's a 0, notice these are just opposites. So that says that if both of the first 2 are 1s, the output is completely controlled by C, and it happens to be the inverse of C. So knowing that, we don't need to consider C as one of our inputs. We can simply say A and B are the 2 we care about, because if they're both 0, 0, the input is a 0. If they're both 0, 1, the input is a 1. If A and B are 1, 0, the input is literally whatever C is. And if they're 1 and 1, the input is what the inverse of C is. So we've managed to take our truth table of 8 lines and reduce it to a truth table of 4 lines. And this is a very, very useful thing. One thing, it'll make your device faster because you've got smaller multiplexer. And also it simplifies looking at the circuit to understand what's going on once you get used to looking at how this would be indicated. So an advantage we have here with this is that an 8-input truth table can be done in a 2-input multiplexer. For a 16-input truth table, it could be done in a 3-input multiplexer. Yeah, you go, oh, that doesn't look like a power of 2 to me. Well, let's think about this for a second and how we would go about doing that. Let me see if I have a whiteboard page available over here. Oh, well, actually, let me redo that. There we go. Okay, so let's assume we have a truth table which has the values 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0. Now, from observation, you should be able to see that if we slice these off into 2s, the first 3 are always identical. So in our multiplexer, let's draw a multiplexer over here just for the heck of it. It's going to have 8 lines. And it's going to have 3 address lines, A, B, and C. And of course, the top line up here is 0, 0, 0. And the bottom line will be 1, 1, 1. Because there's 8 things here, 8 things there. And then over here will be our Y, which would be the output. So now we're asked to wire this in. We could have made a 4-input, right, with 16 inputs and just written this next to it. But we're reducing it by 1 power 2. So raise your hand if you think you can tell me what the first value I'm going to write here is. Dante, what do you think?
Would that be not D?
Well, ask yourself, does it match D exactly?
No, it doesn't.
0 match 0, 1
Oh,
match 1?
sorry, so it's D.
Okay. Next one, Renee?
Not D. Not D.
Right, it's the opposite of that, so it'd be not D. Mikhail, what's the next one?
Also not D.
Right, it's a not D. Anybody else want to take a shot here? Mohammed, what's the next one?
Oh, that would be D.
Okay. Samir?
Would it be X?
Well, it has to be a D, a not D, a 1, or a 0.
I'm gonna do a 1.
Okay. And then this guy, then, of course, would be a 0. And he matches D. and he's the inverse of D. So what do I do with these numbers I just wrote down? Who wants to tell me? Robert?
Those go on to the 8 inputs on the left side of the multiplexer.
Right, so the first one over here would be a D. The second one would be the not D. Then another not D. And then another D, a 1, a 0, a D, and a not D. And over here is where the output comes out. So let's assume for a second that I put as an input in 1, 0, 0. Which line in the table am I looking for over here? Well, it's going to be the one with A, B, and C is 1, 0, 0. So it's this pair here. So which of these two lines do I need to look at? Well, it's going to always be a 1. So we know a 1 is going to come out. If I had said, instead of 1, 0, 0, I had said 1, 1, 1, we would have seen it's this. So it's going to be dependent on D. And whatever D is, since we're really putting, remember into our problem, we're putting 1, 2, 1, or we're putting 1, 1, 1, 1, or we're putting 1, 1, 1, 0 in. One of those is going in, but we're stripping this guy off and sending him to the inputs on the data lines. And we're keeping the other 3 around to go down here. So we were given 4 inputs. We knew which of the 2 lines we wanted, but those 3 selected which of these we were picking, and then D might or might not be routed through to help us get the answer. Let's try another one. Let's build that out of a multiplexer. So try to sketch your thing. So what you'll be asked for eventually with these would be the equation, which describes, each of the inputs. What D0 is hooked to, what D1 is hooked to, something like that. Okay, well, let's do the same thing. We're going to use A at the bottom of our multiplexer. Y will be over here. We can only pick 2 things, 0 or 1. So we have D0, we have D1. What are we going to hook to these 2 lines so that the right thing comes out? Caramel?
B on the top one and 1 on the bottom.
Are you suggesting that we hook a B, that looks like a 0, a B up here, and a 1 down there? If you agree with him, give a green circle. If not, give a red, red circle. I was thinking you had red boxes, you don't. Okay, it says, we have a 2-digit number coming in. Let's say it was 0, 1. We're going to route the 0 over to this pin. And it's going to pick the top line. The top line will use B if it has B or not B to the left of it. So B is going to be pushed in there as a 1. So what's going to come out the other side is a 1. Is 0, 1, and 1? Well, yes, indeedy do it is. What if we were told to do this using a 2-input multiplexer? We did it with a 1-input multiplexer. How about a 2-input multiplexer? Well, how many things am I going to put down at the bottom here? Somebody raise your hand and tell me. These are the inputs, and I said a 2-input multiplexer. This is like the easiest question of the night. Even I can get this one right. Basu?
It's 2.
2. Okay, these are 2 inputs. One is A. One is B. So for a 2-input, how many data lines are we going to have? Robert?
We'll have 4.
1, 2, 3, 4. This is Y over here. So what will we wire to these 4 things right here if we want to do this truth table? Mikhail?
Would it be 0, B not being 1?
Well, in this case, since we have all 4 lines, we're going to just do 0, 1, 1, 1. We don't need to code B over there because we've already coded it over here. Let's do one more of these, and then I think it'll have sunk in pretty well with you guys. Okay, let's implement that using the smallest multiplexer we can. Work that on a piece of paper. I'll try to label this. It's going to be hard to label because I'm writing with this pen, but we'll see what we get here. Actually, you know what? I think I have one of these. Now I'm getting excited. Let's see if I got one of those. I do. Now, we obviously could build this as is. 4 input, right? So we know one of the things we could do is it could have 4 down here, 16 on this side. But we also know we can always reduce it by 1. So we could get it down to an 8 by 3. Question now is, can we get it better than that? Okay, who wants to tell me what I can circle inside my Carnot map here? I'm telling you, I would not want to be in a gunfight in the Old West with Robert. He is the quickest draw on that hands up thing I ever saw. He must keep his extra little toe or something sitting on the keyboard. Basu, what can I combine?
You can combine 4 of those in the middle and 2 on the separate.
So I can combine these 2 together?
Yes.
Can I do better than that? Scott, what do you think?
Okay.
Okay, sorry.
No, go ahead.
I think we can combine 4 of those again. The left 4.
That is the left 4.
I'm sorry,
Okay,
right.
right 4?
Yes.
Okay. Okay, I would agree with you there. So what is the equation for this, Scott?
Y equals BD for the red guy. Or BC.
Okay. So does that help us? Have we reduced anything? What do you think, Robert?
We now know we only care about two variables. So we
Well, I
could
see
use.
3 of them here.
Oh, yeah, sorry, 3.
Okay. So we could say our table has as headings B, C, D, gives us Y. And now to our advantage of this is that now we have 8 lines in the table, meaning that this is the non-reduced form, meaning we should be able to get it down to 4 on that side and 2 underneath. So let's see if we can do that. Let me go back over here and let's try to move this truth table into this one here if I can figure out how to do it. Okay, where do these guys go in terms of this table now? If B and D are both a 1, well, actually, let's erase all the answers. The table now is no longer ABC, it's BCD. And the first case says wherever B and D are both a 1. So if the first and the last one are a 1, that's here and that's here. Anywhere else? Okay, let's say no for that. I'm trying to see the other screen as well. I'm moving this up and down. And the other is BC, meaning the first 2 are turned on. So that's those. So what we've said is all the rest of them are zeros. So if that's the case, then we should be able to take every 2 lines, because the first 2 are the same, right? And we should be able to now do a multiplexer which has 2 on the bottom, which means 4 down the side. So here's our multiplexer. It has 2 inputs, and those 2 inputs are B and C. Our output is Y, and 2 things can only address 4 lines in. So this is the first pair, the second pair, the third pair, and the fourth pair. So see if you can figure out what I should hook to each of these lines. What are the 4 values I need to use here? So this would be the answer to a question, right? Somewhere inside of some parentheses, or Engelbrecht would be saying D0 equals something, D1 equals something, D2 equals something, and D3 equals something. We close our parentheses. So what does D0 equal? Well, in the case where they're both zeros, it's always a 0. The case where they're a 1 or 0, 1 is always a 0. In this case right here, where it's a 1 and a 0, it matches D completely. So this is D. And finally, the last one is always a 1. And this would be the answer you'd submit to a problem like that. But you would have reduced that thing, which looked originally pretty horrible, down to a very simple multiplexer. Any questions about that? Okay, well, you need that in your toolkit, certainly, as something you can do. This is the way a demultiplexer would look. Still, we have 2 address lines. We have the data line coming in This basically is connected to the Y on the other one. And then this is the actual output, which is being selected. So D goes here, D goes here, D goes here, D goes here. The function for this is basically intuitive, what you'd think it would be, that we include D as kind of the leading bit of the DAB trio here. So the data coming in is conditioned by whatever the value A and B are. If D is ever a 0, the only thing that can ever get through is a 0. If D is a 1, the only time a 1 will come out is when the values of these force one of these to be selected. So 0, 0 would cause these both to become a 1 internally. D would be a 1 if we wanted a 1 here, and it would be a 0 if we wanted a 0 to appear here. I wouldn't spend a lot of time thinking about demultiplexers, but I got a couple slides, so I'm going to show them to you anyway. And then finally, this is the way one might be wired internally. D selects which gate we're going to be able to turn a 1 on in, and it goes to all the gates all the time. So all the gates are potentially able to pass D, but they can only pass it if they get addressed by A and B. Now, I think you can download these slides. So hopefully you've been taking good notes and the download would be helpful. I think if you go to the website, and I think it's called /M_ux.zip, mux.zip. That looks like it. So it's located at https://cos231.drbco.com/mux.zip. You might want to download that and let me know that you got it. Okay, while we're here, let's download another one. Download one that's called bus.zip. I think it's a capital B. It is indeed. And then you can kind of follow along in there because there's some transistor problems we have to look at. Okay, let me clean my windows up a little bit here, and then we'll go on and talk about bus architectures. Okay. What is that? Oh. Okay. First thing we're going to look at is we're going to look at something called the open collector output, which is this circuit right here. Now, if you recall, when we looked at an inverter, let me pull up an inverter real quick here. I guess I have to do that. The right-hand side of the circuit is significantly different. Do you remember we had one transistor here and another one here? One is on all the time, one is off at the opposite times. Everybody remember that? Okay. Now, again, don't worry about the values of the resistors and things. Just conceptualize about this for just a second. In the case of the one on the right, if we made the output a 1, current flowed down and out the pin. This is if our output was a 1. If our output was a 0, current came into the pin and went to ground. So of course, since it's such a short route here, we could pull in 16 milliamps, whereas we could only get 400 microamps of current flowing if it was a 1. So this always was connected to either a 1 or a 0 for the next stage of circuitry that might be following this. The open collector behaves a little differently. On the open collector, if we assume for a second that the transistor has been turned on, that means we have current flowing through the base. We're going to get approximately a 0.7 volt drop here. But this voltage right here is going to be pretty low. Current can still flow into the chip to ground. That's not going to be a real problem for it. Now, open them up again. Let's assume that this transistor is turned off. Can you see that output would not be able to get any current from anywhere? Also, this is not hooked to anything, so the voltage is just kind of something, but we don't know what it is, but it certainly can't draw any current. That can't happen. So unlike the one we saw in the last illustration there, the inverter, TTL inverter, this TTL compatible device here allows us to sink current into the chip when we have this transistor turned on. And since this is a buffer circuit, if there's a 0 here, we get a 0 there. But when it's high, nothing comes out. Now, is there a use for that? And that becomes the real question at hand. So let's develop a use for it here. Let me grab my whiteboard. I'm going to place a box here and a box here. I'm going to hook a wire between them. Now, I'm using this guy as an output and this guy as an input. Now, we just said that this guy, if he's looking at this guy's signal, will only know if the guy is putting out a 0. If the guy's putting out anything else, this guy will be confused. So you go, well, that doesn't sound like that would be a really useful thing to do. So let's take, and instead of just leaving the circuit as a wire going here, let's add what's called a pull-up resistor right here. I'm going to call it a pull-up or a PU resistor, pull-up. And it's going to be hooked to, let's say, plus 5 volts. So if this guy doesn't connect to anything, meaning he is in that open collector state, meaning he's not connected to the collector because we're trying to produce a 1, that means that this guy is going to get input instead of from him, from and through the pull-up resistor. And so by default, he's going to see plus roughly 5 volts. And you'll continue seeing that until this guy produces a 0. If this guy produces a 0, of course, current can flow through the resistor to 0, he'll see a 0. So it looks like we just fixed the problem of when he's looking at this guy, he can only see when he's writing a 0. He can never see when he writes a 1. But that doesn't seem to have bought us anything. But then somebody comes along. I don't know who's one of my bright people in here. Scott comes along and he says, but can't you add a second guy producing output? And you guy go, well, that's the silliest thing I ever heard. 2 guys can't talk at the same time. We wouldn't know who was talking. And Scott goes, well, maybe we would. I think about it for a second and I go, well, you know, Scott, you might be right. Let's put a second guy down here. Now, let's set up a situation. Neither one of these guys are talking right now, right? So they're not producing any value. They can't produce a value. But the pull-up resistor has pulled this point right here up to 5 volts. So the guy doing the input can see 5 volts. Now, if either of these two or both produce a 0, current will flow, but this guy's going to see a 0. So we could hook many guys as we wanted to up to this bus, and since they can only write 0s, they can never cause a problem. It's not as if they could write a 0 while the other one's trying to write a 1, because the only signal they can ever write is a 0. Now, they all could write a 0. One of them could write a 0. But if any of them write a 0, they overrule the pull-up resistor, and this guy, instead of seeing 5 volts, sees 0 volts. And that's the purpose of an open collector output. The open collector output is intended to allow us to hook many of these outputs together and have people looking at it and not have anything blow up because they did it. Everybody kind of see how that could lead to us being able to have multiple guys writing at the same time? Now, that doesn't mean we're going to make sense out of what they said, because if all of them are trying to write 0s and one of them wanted to write a 1, the only way you can write a 1 is basically to release the bus, right? You just simply don't write anything, and you assume the bus is being pulled up. Well, it's not being pulled up if somebody else is writing, but no damage can occur. So we're on our way to being able to let multiple people be able to hook up together. This multi-structure of multiple people writing and multiple people listening, because we could have other guys over here listening as well, is called a bus. And it's a very common construction inside of microcontrollers and lots of electric circuits. So let's take a look a little bit at how a bus might really be implemented and how we can improve upon the design we have right now. First of all, let me tell you, in practice, this can actually be used, because the problem we all really solved was Any of the boxes can write 0, and if they release the bus, they're writing a 1 because the pull-up resistor is writing a 1. So all we have to do is discipline them into saying only one guy of you at a time can write. We could control that by having them hooked to some sort of a sequencer. And a sequencer could be built just as a counter out of flip-flops or some sort of timing mechanism that said it's your turn, it's your turn, it's your turn, it's your turn. And as long as the inputs knew whose turn it was, they'd be able to know they're receiving data either from 1, 2, or 3. So keep that in the back of your mind. We're not doing much with this because it turns out that it's an older design and there's a better design, but it still works. And in cheaper designs, this might be the best solution. Instead, let's look at this guy. This has something in it which we call tri-state logic. So the Boolean output here is going to have one of 3 values, not 2. It's going to be either a 0 or a 1, which we know about, or just like the open collector when it wasn't connected to the bus, it's going to be in what we call Z state. Z stands for high impedance. Z is the symbol for impedance. And high impedance basically means I'm not here. So that's the third choice you could have on an output, right? The output's putting out a 0, it's putting out a 1, or the output isn't even there. Now, it may physically be there, but as long as it's putting out a signal from which I can't source or sink current, it's effectively not there. So this is the way an output might look on a buffer being a device that just simply takes a regular 0 and 1 signal and turns it into one that can be 0, 1, or high impedance. We sometimes also call this floating. Floating means we're not giving out a valid value, and we're just kind of hanging around. So how does this work? Well, we put in our data at D. The data, the tri-stated data we get out is gotten out at D out. D in is always either a 0 or a 1. D out can be a 0, a 1, or a Z. So we have an enable pin. When the enable pin is asserted, meaning it's high, D passes through. So D is a 0 or a 1 here. It will be a 0 or a 1 here. If, however, enable is low, meaning we're not enabled, D out will have a value of high impedance, or Z, regardless of the value of the input. Okay, let's work our way through all 4 combinations of those signals and see if we can determine what the transistors are doing. So put on your transistor hat, your little Mr. Wizard glasses and everything to be ready. And let's first of all, let's put a 0 on enable. Oh, well, actually, let's do the other one first. Let's put a 1 on enable. We'll enable it first. And let's put a 0 on the input. Now think what the transistors have to be doing at this point. When you think you know what this transistor is doing, raise your hand. Scott, what do you think this transistor is doing?
I think that transistor will be saturated.
Okay, so you think it's going to be on.
So it'll be on.
Okay, so let's mark that as on for the moment. Now, if it's on, somebody else tell me what value is going to be right at this point right here. And Scott, if they go 5 seconds without their hand going up, you can pop yours back up. Scott, what would we get for a value here?
It'll be low. Let's call it 0.
Yeah, it'll be roughly 0 because this 0.7 here and that pulled down, we know we got a little tiny if it's saturated here, but roughly this is roughly 0 volts. Which says what about this transistor? Here am I?
It would be off.
Right, we can't get anything from 0 to ground, so it's basically as though that line is cut. This stuff doesn't affect the circuit any longer if this is a 1. And that's going to be true if this is a 0 or a 1, it won't matter. So if both are enable cases, we know what these transistors are doing. So we're going to put a 0 here. What else do we know? What else can we determine? What's the value going to be right here? Mohammed?
Will it be high value?
Give me a number.
Around, so it will be 4.2 or 4.3.
Okay, well, Scott, what do you think?
I think it's going to be, I was going to say 0, but now I'm not sure.
Okay, well, let me ask you about this part of the circuit here. We've got 5 volts going through a resistor, going through a diode to ground. What's the drop across a regular diode?
That'll be 0.7 volts.
So if we got 0.7 volts on the base of this, what's 0.7 lower than that?
That'll take us down to 0.
So we would see a 0 here, which is exactly what we expected to see if we had a 0 there. Okay, so we solved the 0 case. Let me put a fresh one of these up so we can put a 1 there. So we said there was a 1 down here, basically cutting this piece of the circuit off. This had a 0, we got a 0. So now we're going to put a 1 here and see what happens. Robert, what value will be here?
Roughly 5 volts because it doesn't have a path out through DN anymore.
Okay, well, we may have another path. Look at that for a second and see if there's any other way we could escape. Well, how about through the transistor? And we have a path that goes through the transistor like that?
Yeah.
Okay. Then if we did that, what we know is that even if we don't know what the value is right here, and the value right there. We know they're 0.7 different from each other, right? Would you agree with that?
Yeah.
Okay, so we got 0.7 different. That means the transistor is turned on. If the transistor is turned on, what happens to the collector emitter? Somebody raise your hand, tell me in a transistor that's fully saturated and turned on, what happens to the collector and the emitter? Robert?
Electricity flows through the collector and out the emitter.
Yeah, but what's the difference in their voltages?
I'd have to look back at my notes.
Saturated transistor, what's VCE? What are we planning for, Scott?
It's going to be very minimal, like 0.1 volts.
Right.
Call it
Okay.
zero.
So if the transistor's turned on and to get from here to here is basically the same thing, what's this guy hooked to? He's hooked to 5 volts. So that means the bottom of this at 5 volts. Won't really be 5. It'll be a little bit lower because the real drop here is probably bigger than, it's enough to keep us with our 0.7 coming backwards, not to say oversaturate. But in just things, we know the transistor's on. We know this point has to be 0.7 higher than this. So this can't be 5 and 5.7. So it's 4.3 maybe. But it's going to be whatever the difference is dropped across the face of that transistor from 5 volts down to whatever we had. Well, if it's that value, it's a 1. We needed a 1. We got a 1. Okay, make sure you can explain those two. Those two cases are the interesting ones. Anybody have a question about that? Okay, well, let's try now what happens if we disable down here. So let me open another one of these up. So I'm going to put a 0 down here. What's the status of this transistor right here? Patricia?
It would be off.
Okay, so this guy now is going to be off. What's the voltage right here going to be?
5 volts.
Well, think about.
Oh, no, sorry, 0.
0. Well, 0 is down here.
Mhm.
How much higher is the base than the emitter if the transistor's turned on?
A 0.7 higher.
Yeah, so we get 0.7 volts right here. But the transistor is turned on, meaning we're basically pulling this spot right here down to ground. And if we pull this spot down to ground, we just grounded the base of the transistor, which means the transistor is off completely. So it doesn't matter what the value here is. We can't pull any current that way because there's nowhere to get it from. We're at ground. And we can't push any current anywhere because it can't go that way up through the thing because the transistor's turned off. The only way we could get this to match would be if we could turn the transistor on, and we can't because this is ground. So basically, we've turned off the transistor completely, meaning it looks like a brick wall, and the output here is a Z, meaning it's the same as if we were not even connected. Now you might say, well, what good is the thing? Why would we even want one of these things? They sound like much too hard. Well, the reason would be that most of the circuits we've designed, remember our AND gate that we have? We can't take that output and take another guy, maybe there's an OR gate over here, and tie their outputs together and then look at them, because if he's doing a 0 and he's doing a 1, something's going to catch on fire. What we need to do is we need to have whichever one should not be seen right here, right now, produce a Z. So what we're going to do is, let's pretend like we were doing this to an inverter. After the gate, we're going to put something that looks like an inverter. It's a buffer, but we're going to give it a third pin. And the third pin is going to be the enable line. And that's going to be the thing that tells us we're tri-stating it. So what's on this side is 0s and 1s. And then what's on this side is 0s and 1s, as long as that's enabled, but a big Z there if this is disabled. So these tri-state buffer chips, or 3-state buffer chips, are going to be put lots of places inside our CPU design, because we're going to have multiple things trying to write to the same inputs. Any questions about this picture before I take it down? You have a picture in that handout I gave you, so it is not as if you can't reproduce it. And I would try to work my way back through the problem as part of your studying, because you know you're going to get one of those on your exam. Robert, you have a question?
Could you use something like this, for example, in the state machine thing that we made, to set the very first state and then have it go through this for the first time and then the regular logic board for the second time?
It would be possible to do that, yes. Okay, I'm going to delete this for now. And I'm going to go grab the next slide. Now, we've seen this guy before, at least most of him. Remember up here we had a controlled buffer register. We could load the buffer register all at once by asserting load and waiting for a clock. We could clear the buffer register to all 0s asynchronously. And if we didn't load or clear, we would just simply recycle Q back around so it would keep the same value. Its outputs, which are on Q, are 0s and 1s. So we couldn't take these guys and then create another one of these and hook all their outputs together, because if this guy tried to produce a 1 and the other guy tried to produce a 0, we might cause a fire. At best, or at worst, we'd cause a fire, I suppose. At best, we would get some sort of a signal which might be halfway between a 0 or 1. So instead, externally to this, we're going to hook a tri-state buffer at each of these locations. Now, that circuit I showed you is one of these. So we would have 4 of them. Normally, they come 8 to the chip, but we would use 4 of them here. Notice here's the enable line. And the enable line will take the 0 or the 1 and pass it through if enable is a 1. And it will block it, won't change it. It'll just hold on to it, but not like a flip-flop. It'll just keep whatever value it has on its input until we enable it, but produce a Z, basically disconnect these lines from the bus until such time as we would need them later. Does everybody understand this picture? The stuff back, whoops, I shouldn't have drawn the line like that. Everything that way of this could be any circuit. The stuff on this side is how we buffer it to make it so its outputs can be hooked together with other speakers, other people that can talk. Now we can simplify one of these things and kind of make them generic by drawing our box. So I'm going to stay zoomed in here, even though there's more down at the bottom. Each of these is a buffer register in our case. Now, by buffer register, I simply mean that it can hold some data. I'm not meaning necessarily it uses flip-flops to do so, but it can hold some data. The function is not described here other than just to simply say we have box A, B, C, and D. Now we have another shared resource in the picture, which are these 4 wires that go down the center of the screen. We call them the W bus. W stands for wire. It's a wire bus. It literally is 4 wires in parallel with each other, and we've allowed to have some connections to those wires. Now, the wire bus can be of any width that we choose. Our design will be helped or hindered by the number we pick, but they're intended to allow us to pass data or share data among the boxes which are pictured in the diagram. Now, all of these boxes have full functionality. And let me explain that a little bit to you as we go along here. We'll look and focus in on box A to start with. In box A, we have 4 lines hooked to the bus on one side and 4 lines hooked to the bus on the other side. Let's call these wires over here inputs. And let's call these wires over here outputs. Now we know that the box can read and write to those 4 wires. Reading is called in, writing is called outputting or out to. Now we don't have to be able to do both, and in a circuit we would not have to necessarily be connected to the same bus. We'll probably be connected to somebody, but we may not be connected to this particular bus. But in this case, all of the inputs are hooked to all of the bus lines. All of the outputs are hooked to all of the bus lines. Notice W0 is on the right-hand side. That's the least significant bit. W3, which is the 4th bit over, is on the left side. That's the most significant bit. Same thing with our picture here. Most significant bit goes in here, W3. W2 goes here. W1 here. And W0 here. Same thing on the other side. W0, W1, W2, and W3. Now, because we're calling these boxes bus type registers, meaning they can read and write by way of a bus, we have to have some control signals which allow us to say, are we reading or writing right now, or neither one? So if we want to read, we need to assert 2 signals. Load and the clock signal will be used. So if we're going to read from the bus, meaning we're going to use the input lines, we're going to have a load signal and we're going to have a clock. Notice our clock is going to be edge going or edge triggered. Might be inverted, might have a little bubble on it, but it's going to be an edge triggered clock. Load might be an inverted load. Enable down here later also might be inverted. But if we're going to read from the bus, we must have a load, we must have a clock. If we're going to write to the bus, we must have an enable signal. And our outputs must be tri-stated, meaning that we can appear to not be here to somebody if we're not the person who has been elected to speak on this particular clock cycle. So if I were a box that could only read from the bus, I would still have 4 wires coming in. I would still have a load. Let's put an L here. I would still have a clock, but I would not have an enable, and I wouldn't have the 4 wires going out. So if this is a read only, I'll put RO for read only. If I'm write only, I would have an enable signal, and I would have 4 lines that go back to the bus. If I do both, I'd have 2 signals, a load and an enable, and I'd have a clock as well, and I'd have 8 lines in this case. If this were 16 wide, I'd have 32 lines. 16 in, 16 out. Now, in our protocol, we are only going to allow one person at a time, one box at a time, to write on the bus. So at any given point in time, only one enable can be asserted. So I would never have 2, because when we're not enabled, all our outputs are tri-stated. When we are enabled, we're producing a 1 and a 0 on every line. So we can have one writer. Or we can have 0. And we can have any number of readers. So we can have 0 or 1 people writing to the bus, meaning somebody can, nobody can't. We can have any number of readers. Now, it doesn't make sense if nobody's writing for somebody to be reading. And this is active at the moment. I mean, this guy can be a reader or a writer. He can't be both at the same time. Well, actually, he could be both at the same time. He would simply read what he's writing. I don't think anything we do ever causes one to do that, but that would be a legal condition. At the case where we have no writers, nobody should be reading. Okay, give me any questions you might have about what we just discussed there. Because we're going to need to effectively build a processor, be able to have multiple functional boxes talking to each other. Okay, now we can simplify drawing all these lines. That would be the next picture. Anytime I have lines that I'm reading on, I can just group them all together and have an arrow pointing in. If I'm writing to the bus, I can have an arrow going out. Now, to be honest with you, occasionally, as long as the same number is done, you may see a single arrow going to a box which has heads on both sides, which just means it can read and write. As long as it's the same number of lines bidirectionally, it doesn't matter. Now, we don't know in this picture how big the W bus is. So let's say it's 8 lines wide. We would indicate there's 8 lines here, or else we might write 8 lines inside of this. You might also see some numbers here. 8, 8, 4, 8, 8, 4, 8, 8. Now, by convention, if we don't read all of the lines or write all of the lines, the ones we are reading and writing to are the ones on the right-hand side of the bus. So if I had 8 bits, and this guy needed to read 4 bits, the 4 bits he would get would be those 4 on the right. If he read 8, he'd get all 8. If we were writing 4 bits, the ones we would write would be the 4 on the right-hand side. It's just a matter of how they get wired. It's also possible for these to have additional arrows coming out of them, which go to boxes that are not participating with the bus. In which case, these signals very often are not timed. They happen all the time. And you kind of have to study the diagram to know exactly what's going on when that occurs. Okay, now let's take and look at the process a bus might go through in order to transfer some data. First of all, let's look at a single clock cycle. We have a clock cycle that is low to start with, sometime in the future goes high, and stays high for approximately the same length of time it was low. This is one clock cycle. So this is one clock cycle. It also will become for us, I'm going to put this in parentheses for now, one T state. STATE if you can't read it. And we'll talk about later what that means. But this is a significant chunk of time, one T state. We know how to calculate the period and the time and all that. But what's more important is when we're moving things from box to box, all of the signals that indicate what you should do, except for the clock, are always asserted at the beginning of the T state or the beginning of the clock cycle and held throughout the entire clock cycle. So let's just call this the control signals. I just CS for control signal. It's always put on the boxes at the start of a clock cycle, and it's removed when it goes low again. So it's held for a complete clock cycle. The clock, which is what's hooked to this box here, in this case rising edge, always reads or writes data on the rising edge. So that's where read or write occurs. So let's assume that I wanted to load something into box A that's on the bus. Now, we don't know how it got on the bus, but there's some stuff on the bus right now. In order to load it, I would need to have somebody turn on LA. And halfway through the clock cycle, the clock would tick, and whatever's on the bus at that point would get transferred into A. When the clock fell again, LA would be removed unless it was going to be loaded again. So this timing of when things occur is very, very critical. And we control it by using control signals at the start of the T state on the low clock, the 0 of the clock. Data gets transferred on the 1 of the clock when it goes high. The low signal is held for the entire T state, and it changes again on the next clock cycle. So let's move some data around here. Let me erase some of this. I don't know if I've run out of redos or not. I did. And we know how many redos they have. Okay, let's assume for a second that A contains this binary value 0, 1, 0, 1. B contains 1, 1, 1, 1. We don't know what's in C. And D contains 1, 0, 1, 0. We are just prior to the first edge. The bus, because nobody has enable asserted right now, has, let's say there's 4 bits, has 4 Z's on it. They're going to look like 2's for the moment. So lights, camera, action. What we want to do is we want to move the data that's in A into D. So the moment the clock drops right at this cycle right here, just as soon as it goes low, we have to assert 2 signals. We want A to write. We want D to read. What signal do I need to assert for A? Raise your hand if you can tell me. Robert?
Enable.
So at this point, enable A gets asserted. And somebody else tell me what signal gets asserted on D. Patricia?
The load and the clock.
Just the load.
The load.
Okay. Load D. So enable A, load D. Sometime in the future, the clock is going to tick. But the moment I put that on the control lines, this guy has a load signal. I'm sorry, has an enable. Enable turns off the tri-state buffers. So his data is on the bus. So the bus now contains 1, 0, 0, I'm sorry, 0, 1, 0, 1. Right here, the bus got changed because we said enable A. Halfway through the clock, since a load is waiting for the clock edge, this data, halfway through, just as the clock rises, gets transferred in, and this gets replaced with 01, 01. Assuming nothing happens when the clock drops, except the signals get taken away, this guy no longer is driving these on the bus, so Z's reappear. And since nobody has enable asserted, nobody will load even though the clock ticks again. But we successfully transferred what was in A over to D. Now see if you can tell me what signals we have to assert in order to get what's in C. I'm sorry, let's make it from B. We want what's in B transferred into C. See if you can figure out what signals I need to assert here, and also tell me what's going to be on the bus as soon as we assert those signals. Okay, Scott, what signals should I assert?
We'll assert enable B and load C.
Okay, and so what happens to the bus? It's going to happen immediately. As soon as I assert enable B.
The bus will contain 1111.
Right, the Z's go away because we just enabled it. It has to be 1s and 0s. And they'll stay there. The C doesn't change as long as the clock stays low until the rising edge. Now, Patricia, what goes into C at that point?
1111.
Right. So now C contains 1111. And that's the basic bus architecture that's on the computer you're sitting there using right now. Basically, things are controlled by a control signal or set of control signals. On our first processor we're going to use, there's going to be 12 control signals. I can't write with this pen. That says control signals. In this case, There's 1, 2, 3, 4, 5, 6, 7, 8 control signals. Now somebody else is controlling the clock, but somebody else knows how to tell the guy that's setting the control signals when the clock goes low, so they'll know to set them right then. Let's take this picture. Let me reload it again, since I've made such a mess of it. And let's get rid of that signal and that one. And this one, those two, and that one. Actually, I'm going to put that one back. Are any of my boxes able to only read from the bus? Only read. Raise your hand if you think there are some. Mikhail?
Box B can only read.
So we got this guy can read. This guy or these two?
B.
B. B has a load, so he can read. How about A?
Yeah, A could read and write.
Okay, but we need to worry about read right now, so that's both A and B.
So yeah.
Okay, but we said only read, so that's not A. So B can only read. The only write guys. Patricia, who can only write?
C and D.
And then we, of course, have the one guy that can do both. What if we had a guy that could do neither? Could he potentially still be a useful box? Or do we have to be connected to the bus? What do you think, Robert?
Well, we would certainly need something to set the control signals.
Right, and he doesn't need to be connected to the bus necessarily. So he could sit over here and control those signals without knowing what the bus is doing because he doesn't care what value's on it. So yes, you could. Could we have anything that loads without a clock? Simple two-letter answer to that one. Yeah, that's right. You can't. If we're going to have a load, we need to have a clock to synchronize with, at least on the bus side. And we didn't define any level-triggered clocks on the other side. So we'll find that they won't be that useful. But this turns out to be an extremely useful architecture. Now, you might be saying to yourself, though, what in the world is going on inside the box? If all I can do is store something in here and put it back on the bus for somebody else to store it, isn't eventually everybody just going to have the same thing inside of them? And this comes into one of the things we haven't talked about too much yet is all of these boxes are going to be assigned some sort of a function. You know, maybe the function they have is take the current instruction we have, decode it, and tell another box, which is the controller sequencer, which instruction it needs to be prepared to execute. Maybe one of them controls LEDs somewhere so we could see our answer. A computer that doesn't tell you what the answer is kind of scary. You know, we don't see that a lot. A computer that only has inputs and never tells you what the answer was that it computed. So we're going to find, and we'll go into this when we talk about the SAP-1, which is a very important night to spend with us, which is, I think, the evening after the test. That's one of those coming of age things. You become a real computer scientist after you understand the SAP-1. Okay, do we have any questions about anything that we have covered tonight? Okay, I want to do one more multiplexer problem before we go because I want to make sure because we're not going to get to have time to do them again on Thursday, really. We might during the review on Thursday, but on Tuesday, listen to me talk here. On Thursday, we have a review, so we might do some. On Wednesday in class, we're doing a different topic. Okay, so what am I looking for here? The whiteboard. And let's do this one. Let's say we have this function. And what we want to do is make the function do its thing from a multiplexer. Well, I finished writing those on there. See if you can do the first obvious part, which is there is some combining, and let's write the minimum sum of products down. Anybody want to tell me what y is equal to? Mohammed?
It will be not A, not B, or A, B.
Okay, so my truth table, how many entries should I put in it? ABC, that's 2 to the third, that's 8 entries. Dante?
Would it be 2?
Well, we have A and B only, right? There is no C, so there's no point writing it out as an 8-element truth table. We have A and B giving us the values of Y. And we have 0, 0, and we have 1, 1. Oops. And in here we have zeros. We're going to build it using a multiplexer. Let's say the teacher told us to build it using a 2-input multiplexer. We know we can build it with a 1-input multiplexer, but the teacher said build it with a 2-input multiplexer. How are we going to do that? Somebody tell me what I need to draw here. Dante?
For 2-input multiplexer, you would just have the A and the B on the bottom, and then the left would be just made up of our basically our truth table, the 0, 0,
Okay,
0,
so
1,
this is
1,
A
0,
and
1.
B. Okay. And we'd have 4 coming down here. Now we know we can do this better than this in terms of number of things, but the teacher told us 2 input. So this is 0, 0, 0, 1, 1, 0, and 1, 1. So what goes on the left-hand side over here? You got your hand up still, Dante. Why don't you tell me?
The left-hand side would be. See, I don't think I know. What is it? Can't remember.
It's just going to be these values right here.
Okay.
1, 0, 0, 1. Of course, we have y over here. A test question might ask you what's the equation for it. And so in our case here, the equation would be d0 equals 1, D1 equals 0, D2 equals 0, and D3 equals 1. And those would be inside of angle brackets. Don't know if I can get another one in front of it there or not. Oops, I missed it the wrong one. But you get the idea. Okay, everybody clear about that? Then, unless there's any other questions, last call. Then I will see you guys on Wednesday night. And we're going to cover kind of hardware compilers and the modern state of development. And that should put us in a really good position for an exam next week. So I will see you guys at 6 o'clock on Wednesday. Have a good time until then, and make sure you stay healthy.
Good night, Professor.
Good night.
Have a good night, Professor.
Good night, Professor.
You too. Bye-bye.
Good night, Professor.
Bye-bye.
Good night, Professor.